Hello everyone, welcome back. In this video, I will be covering section 2.5, continuity. The function is said to be continuous at a number a if limit of f of x as x approaching a is equal to f of a, which means that you are able to plug in a in the place of x. So the limit value of the function is same as the value of the function at a. Okay, the limit of f of x at a is the same as the value of f at x equal to a, or the y coordinate of the value of f at a is f of a, which is the y coordinate at a. Notice that definition 1 implicitly requires three things if f is continuous at a. F of a is defined, that is a is in the domain of f. Limit is x approaching a, f of x exists. Limit is x approaching a, f of x not only exists, but it should be equal to the value of the function at a. Okay, these three things should happen. Figure 2 shows the graph of a function f at which numbers is f discontinuous and give a reason. So even if any one of these three conditions fail, then it is discontinuous at that point. So let's look at 1. So clearly there is a hole there, so it is discontinuous at 1. In other words, it will not be satisfying f of the first condition, f of a is undefined. And also at 3, because left limit and the right limit are not the same. And then at 5, the limit exists, but it is not equal to the value of the function at 5. So let's write down those numbers. Discontinuous at what are the numbers? At x equal to 1, at x equal to 3, at x equal to 5. What is the reason now? Reason for each one of them. Discontinuous at 1 because f at 1 is not defined. That is a hole, correct? Hole at x equal to 1. The second reason, discontinuous at 3. Why? So the limit as x approaching 3 minus from the left side is this one. It approaches this number, whereas the right one approaches this number. So the left limit is not equal to the right limit at 3. So the limit does not exist. The second condition fails. Limit as x approaching 3 f of x does not exist because the right limit must be equal to the left limit. The third reason, third discontinuity, x equal to 5. What is happening there? So at x approaches 5 from the right, from the left and the right, f of x approaches this number, but that the limiting value is not equal to the functional value. This is at 5. There is a solid dot which has a value, but the limit value is not equal to the functional value. So it is the third condition that fails. So limit as x approaching 5 of f of x exists, but the value of it is not equal to the value of the function at 5. So the third condition fails. So given a graph, we are able to find out by examining the limits, we are able to say whether the function is continuous or discontinuous at a point. Where are each of the following functions discontinuous? So for A, the figure is already given to you. It's x squared minus x minus 2. That is x minus 2 times x plus 1 over x minus 2. So you're canceling that x minus 2. That means there is a hole at x equal to 2. This clearly tells us it is discontinuous at 2. So the first part, it is discontinuous at x equal to 2. The reason is f of 2 is undefined. There is a hole there. Then the next one is 1 over x squared, part B. This has to be C. So 1 over x squared, x is not equal to 0, and it is equal to 1 at x equal to 1. There is a solid dot here. So here the limit exists at 0. So it is, even though it is said to be infinite limit is x approaching from the right, x approaching from the left, f of x approaches infinity. But what is f of 0 though? F of 0 is something different. So it is not equal to limit as x approaching 0 of f of x. F of 0 is not infinity. It is something different. It's a point here. So that is for the second part, the reason. For the third part, so you notice that the part A and part C are kind of similar. Only thing is there is a redefinition at x equal to 2. So it is discontinuous at 2, but the limit as x approaching 2 from the left of 2 or from the right of 2, the limit exists, which is that hole, where the y coordinate of the hole, but f for 2 has a solid point. So for C, what happens is, limit as x approaching 2 f of x exists, but it is not equal to f for 2. The next one is called an integer function. So you write that with a double bracket here, x. This means if it is integer to the largest integer smaller than or equal to x. What does that mean? If I consider 2.1, an integer, greatest integer of 2.1, now what is less than 2.1? What is the largest integer to the left of 2.1, which is equal to 2? Same way, if you take negative 3.1, so in the number line, so it is negative 1, negative 2, negative 3, negative, let's say this is negative 3.1. What is the largest integer to the left of negative 3.1? That will be negative 4, correct? So this is known as the largest integer function. It is a step function. So when a value of x lies between 0 up to say a value smaller than 1, it will be equal to 0. For an integer, for a function, for an x lying between 1 to 2, but 1 included, but less than or equal to 2, the largest integer in that one will be 1. So it is called a step function or the floor function. From the figure, you notice that it is jumping at every integer. So the discontinuities of this function are So it is discontinuous at all integers. So, namely, 1, -1, -1, -2, -3. So at all integers. So it is discontinuous at all integers. That is the property of the step function. All right. The function is continuous from the right. Continuous from the right at a number a if limit is x approaching a plus f of x equal to f of a. It is kind of similar to the idea of right limit and the left limit, but here we are extending that property to continuity, which means that the limit should not only exist on the right side, but it should coincide with the value of the function at a. And f is continuous from the left at a if limit is x approaching a from the left of f of x equal to f of a. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So if f and g are continuous at a, then the sum of the two functions will be continuous. F plus g is continuous. F minus g is continuous at a. C times f is continuous at a. F times g is continuous at a. F over g is continuous at a, provided the denominator at a is not equal to 0. Okay. The following types of functions are automatically continuous at every number in their domain. At every number in the domain, that part is important. So it is continuous for all values in the domain. Polynomials. You know what are polynomials? So anything which has an integer coefficient, right? So polynomial will be something like this. Polynomials. What are rational functions? Rational functions can look like this, 1 over x minus 2. So remember that it is continuous. It is not continuous at 2 in this example because 2 makes the denominator 0, but 2 is not part of the domain. That's why we say it is continuous on every number in their domain. Radical function. So if I consider x minus 3, it is continuous for all values greater than or equal to 3, because whatever makes the integrand, whatever makes the radicand positive or 0. So the root functions. Trigonometric functions. So it's sine x, cosine x, all those functions. Inverse trigonometric functions. So it is sine inverse of x, cosine inverse of x, and so on. Exponential function. So e to the x, 2 to the x, and all that. Logarithmic functions. So log of x to the base 2, or ln of x, all these functions are logarithmic functions. If g is continuous at a and f is continuous at g of a, then the composite function f composite g is given by f composite g of x equal to f of g of x is continuous at a. In other words, it's the function of a function is continuous, provided the domain is continuous. If f is continuous at g of a, then function of a function, the composite function will be continuous. What is intermediate value theorem? Suppose f is continuous on the closed interval ab, and n is any number between f of a and f of b, where f of a is not equal to f of b, then there is a number c on the open interval ab such that f of c equal to n. More importantly, this is kind of easy to picturize. So let's say you have a graph which goes like that. So if you take a point A here, and this point will be a f of a. and at this point here is b f of b. If the function is continuous, this is a continuous function, let's say, no breaks, no hole. But it's continuous, and you notice that f of a, the y coordinate at a is negative, the y coordinate at b is positive. Because it is continuous, the function should go from negative to positive only through the value 0. That means that there is at least one point C at which there is a root. There is at least one point C between A and B, so at which the function should become 0, where C lies between A and B. So if the n values of the interval, the y coordinates of the n values of the interval change in sign, then definitely there will be at least. So in this graph, you can even have the graph crossing the x-axis more number of times. The graph can also look somewhat like this. So here, this f of a is negative and f of b is positive. So this can happen even the graph runs from positive to negative. Then also it is, the only thing is that the n values of the interval, the y coordinates should change in sign. Then there is at least one root for the function as long as the function is continuous without any breaks or holes. That is intermediate value theorem. Show that there is a root of the equation between 1 and 2. So we have to find out what f of 1 is and look at the sign. And then we have to find out what f of 2 is, look at the sign, see whether the two values change in sign. Then we can conclude that there is a 0 between those two values. So let's substitute x equal to 1. So it is 4 times 1 cube minus 6 times 1 square plus 3 times 1 minus 2. So all I have done is I have plugged in x equal to 1. So if you simplify this, it becomes 4 minus 6 plus 3 minus 2. So it is 4 minus 6 minus 2 plus 3, positive 1. 1 minus 2, which is negative 1. So this is negative. So at one n value, the functional value is negative. The y coordinate is negative. Let's do the same for the next number, f at 2. So I'm going to plug in x equal to 2 into the original. So 4 times 2 cube minus 6 times 2 square plus 3 times 2 minus 2. So it is 4 times 8, that is 32, minus 4 times 6, that's a 24, plus 6 minus 2. So if you simplify, this value will be positive. So by intermediate value theorem, we call it IVT. By intermediate value theorem, we can conclude that there is a root. There is a root. Another word for root is a 0. A root or 0 for the given function f of x between x equal to 1 and x equal to 2. There are some additional suggested problems from the exercise. Some of them are homework, some of them are practice exam questions. And some of these questions are done in the videos, chapter videos. Please check them out. Number 22 and 45 are done. There is a similar problem. Number 36 is done, but I will show number 36 here also in this concept video. And then we will do one more of this exercise. So what is limit as theta? I'm doing number 36. Number 36. The limit as theta tending to pi by 2, limit of theta approaching pi by 2, sine, tan, cosine theta. Sine of tan of cosine theta. So here the property that we use is if f and g are continuous at A, then f composite g will be continuous at A. So it is a composite function being continuous. So this is the theorem that we are using. So for that, f should be continuous at g of A. So the inside one, f should be continuous at g of A is required here. So if you notice this function here, it can be considered as composite function. And tan, see, sine is continuous everywhere, cosine is continuous everywhere. But tan has asymptotes, so it's not continuous everywhere. It has discontinuities at the vertical asymptotes, namely multiples of pi by 2, odd multiples of pi by 2. So as long as the inside of tan doesn't turn out to be pi by 2 or odd multiples of pi by 2, then we can assume that the function is continuous everywhere and direct plugging in is possible. So we can say limit is theta tending to pi by 2, tan of cosine theta. So we will plug in pi by 2. So can we write this as a function of a function? Of course, tan of cosine theta is a function of a function. So you can write, let's say you can consider f to be equal to sine theta and g to be equal to tan theta and h to be equal to cosine of theta, right? So if you consider g composite h, it will be tan of cosine theta, right? Then f composite g composite h would be sine of tan of cosine theta. So it becomes composite of 3 functions. We can consider that way. So plug in pi by 2. All these are continuous. Tan, sine and cosine are continuous everywhere. Sine and cosine are continuous everywhere. Tan is continuous all but odd multiples of pi by 2. It is discontinuous at pi by 2, discontinuous at negative pi by 2. Because tan is made up of sine over cosine. So whichever makes the denominator, the cosine function 0, then it will be discontinuous there. But tan is continuous at 0. Tan is continuous. Tan theta is continuous at theta equal to 0. So when we plug in pi by 2, the interior cosine of pi by 2 is 0, but tan of 0 does exist because it is continuous there. So plug in pi by 2 by using that theorem. So we get sine of, so it's limit theta approaching pi by 2 of sine of tan of cosine theta would become sine of tan of cosine pi by 2. Let's start computing from the inside. So it is sine of, first let's examine what cosine pi by 2 is. As you all know, cosine pi by 2 is 0. So we have tan 0 inside. So tan is defined at 0. its value is equal to 0. Tan of pi by 2 doesn't exist, right? Tan pi by 2, sine pi by 2, or cosine pi by 2. So it approaches infinity there. But as long as the domain is 0, it is continuous there. So tan 0 is 0. Now inside, now we are going to consider tan of 0, which is equal to 0. But now what is sine 0 equal to? 0. So the value of the limit as theta tending to pi by 2 of sine of tan of cosine theta is equal to 0. All right. Whenever they ask you in an intermediate value theorem, you notice that show that there is a root of the given equation. So we know that root, another word, is 0 or the x-intercept. So for these problems, all you have to do is for the first one, you have to consider f of 1 and then f of 2 and show that they are opposite signs. That will show that the function will have a 0 between 1 and 2. So if you look at the intermediate value theorem that we proved, so when it changes sign like that, it crosses the x-axis. So the point where the x-intercept is also known as the root dot 0, right? So here, if f of a negative, f of b positive, the graph crosses the x-axis 3 times here. So what it guarantees, intermediate value theorem, is that as long as the sign changes between a and b, and if the function is continuous, there is at least 1 0. So the root is called the x-intercept. It's also called the root or 0. It's also called a 0, which is nothing but the x-intercept. So in these problems, all you have to show is that the two values, same way here, f of 2 and f of 3 have different signs. Okay. That finishes this section. So I ask you to watch my chapter videos for the problems 22 and 45. The next video will be on section 2.6. So please watch the video, watch my next video on section 2.6.